quantum systems and for the study of quantum systems with memory. So let's get to it. If we can change slides. Okay, what are we talking about? We're talking about open systems. So what is the idea? The idea, we have an observer that is monitoring a system. So the observer here is a hare. This is a Swedish hare, and it's monitoring some carrots. And it's interested, the observer is interested in tracking how the system evolves in time. So it keeps measuring the system and see how some property of interest, some carrotness property, evolves with time. But now, of course, the system the observer is using is not alone in the universe. It's subject to a lot of external influence. And the question is, what is the best description the observer can give of this time-evolving open system? And to focus the idea of what we are going for, let's look at the gold standard that we have in quantum theory. And these are quantum states as represented by density operators. So density operators, as we know, has a mathematical definition, is a positive semi-definite operator with trace equal 1. Now, why is this the golden standard, I say, of a description of a system? Well, first of all, it allows us to predict, to make predictions. So any measurement we can perform on the system will be represented by a set of operators, and we can predict the probability to see one outcome or the other using the Born rule. So the state represents the maximum information we can have on a system if we want to measure it. Now, of course, the question is, how do we derive, how do we find what is the appropriate density operator? And we can imagine two different routes. One is we can have a model. So, for example, we can say the density operator maybe is the thermal state given certain Hamiltonian, or maybe it's a reduced state of a bigger pure state that we have some theoretical reason to postulate. So this is what I will call a modeling approach. However, the really important aspect is that even without knowing essentially nothing, without knowing anything about the system, we can always reconstruct, at least in principle, we can always reconstruct the state from experiment. So the density operator has a purely empirical meaning. So in principle, if we can make arbitrarily many repetitions of the experiment, we can measure in a tomographically complete basis, and we can reconstruct the state purely from experiment without making any assumptions about the model. So in this sense, we can say that the density operator encodes all and only the accessible information that we can have about the system without talking about environment, about other degrees of freedom. Okay, so that's good for if what we are interested in is measuring a system at a given time. And now, what do we do if we have what we are talking about, a system that evolves in time? So in particular, to simplify, we think that we can look at the system at a discrete set of times, maybe even a finite set of times. And now, what most of us intuitively will do is, well, if we want to look at the system multiple times, the best we can do is to describe its state at each time. So the density operator at time 1, at time 2, and at time n. So this is what I call the evolving state fallacy. And to illustrate it, consider this classical example. So these are the weather forecast for Kiev on Thursday. And you can see that on the x-axis, there is time. And we see some kind of state evolving over time. So the state here is the probability that it's going to rain at any given time. And now I ask you a question, given this information, can you calculate what is the total probability it's going to rain on Thursday? And now, well, I could leave you a few minutes to think what is this probability, or I can just reveal what the Google says. Google says that the total probability is 50%. Now, this seems to be very strange, since that there is one given time that probability is 48, and then it keeps fluctuating. So Google is often not really consistent in giving its prediction. Now, the point I want to make is there is actually no formula. Given this time evolving probability, there is no formula to calculate the total probability. And the point is that we are actually missing information. When we're giving this time evolving probability, we don't know what are the correlations across different times. So it could be that these are completely independent probabilities. So the probability that it trains at some time is completely independent of any other time. However, that's most likely not the case. If we have some weather system, then we have some clouds that goes in, and then when the cloud rains, it depletes. And so most likely there is some correlation between each time. And so this 50% will only make sense if this is a very correlated system. And if it rains, say at 4 a.m., then it definitely doesn't rain at any other time. Most likely this is just wrong and Google doesn't really know about statistics. Okay, so this is to highlight the fact that when we're talking about a general open system in time, we really have to keep track in general of temporal correlations. Now, what are we actually doing when we consider a time evolving state? So if we give this quantum description of a state at any given time, what type of information does this give us? So this allows us to calculate the one-time marginals. So this means, in this case, our observer can measure the system at time 1, or it can measure the system at time 2, or it can measure the system at time n. So every time we run the experiment, the observer is only allowed to measure the system at one particular time. And in this case, the state at that time correctly predicts the probability for outcomes at that time. However, as we mentioned before, we are not interested just in that. We would like to consider a scenario where in each run of the experiment, the observer can measure the system multiple times. So this is just one run, and then the observer measures at time 1 and at time 2 and time 3, and so on. And so what we want to measure is actually the joint probability for outcome at time 1, time 2, time n. So this is the information we were missing in the weather example. If we were given the joint probability for rain at all given time, then we will be able to calculate in particular the total probability for rain on Thursday. So this brings the question, what is a quantum process, or what is a quantum stochastic process? So we have said that if we consider this time evolving state, all we can do is reconstruct the marginal probabilities at each given time. On the other hand, we know that the classical stochastic process, as we said, is the joint probability distribution for our variable at all times. And the question is, what is the quantum object that leads to this the classical stochastic process in a limit? Now, what we typically consider, which makes our life much easier, are Markovian processes. So these are processes that are characterized by two time correlations. So if I want to know the probability at a given time, it's only enough to consider it's conditional given the probability at the previous time, and we can reconstruct the whole probability in this way. Now, for this, we do have a very good quantum analog, and this is a dynamical map. So a dynamical map is a channel that sends a state at a given time to a state at a future time, and it correctly leads to the two-time marginals in the classical limit. However, Markovianity is actually a very special case, and as soon as our system is a little complicated, then it's certainly not a reliable assumption. And in fact, in the context of quantum technology, it's more and more appearing to be very clear that non-Markovianity is the rule and not the exception. So many different reports and many different studies have started to highlight the existence of non-Markovian effects in complex systems, in engineered quantum systems. And very often this is not discussed very prominently because it's kind of complicated. However, if we are serious in building a scaled up quantum technologies, then certainly we have to take this into account. Okay, so what is then the general quantum process we are looking at? Well, one way we can look at it is to try to make a model for it. So most generally, we can think that we have some initial state that might be even correlated state between system and environment. Then we make our measurement at time 1. And then between each pair of time steps, we have some Hamiltonian that will involve some interaction between system and environment that will correlate system and environment. So this is the modeling version. However, as I mentioned at the beginning, this is not what I would call a golden standard of a representation, because from measurements on the system alone, I cannot reconstruct this Hamiltonian. My environment might be incredibly complicated, and if I cannot measure the environment, then I cannot reconstruct this Hamiltonian. So if I want to make a demographic reconstruction of the process at this level, it's not yet clear what can I reconstruct. So the goal is similarly to how the Born rule recovers probabilities for one-time measurements. We want to find a model-free formula for our joint probabilities. So something that encodes all and only the information about the measurements we can perform on the system. And here, as I mentioned, the A1, A2, AN represents the outcome of the operations I can perform at time 1, time 2, time n. Okay, then going back to the question, what is a quantum stochastic process? Now, we can see some problems if we want to try to follow some standard approach to model this. If you take some quantum information perspective, typically one tries to generalize joint probabilities to joint states, and then assume that the classical limit leads to the joint probability. However, this doesn't really work in this case because a state typically represents a scenario at a given time. While here, we are making measurements at multiple times. So we cannot really represent it as a state as it is usually defined. And physically, the problem we are facing is that of collapse, or the general fact that the measurement disturbs the system. So if we have our system, it's measured, then after the measurement, we cannot really ignore the fact that we acted on the system. Now, this might seem difficult, but in fact, what we really need to do is to track what is the origin of the problem, and the origin of the problem is essentially causal influence. So the point is that the outcomes in the future can depend on choices of operations we have performed in the past. So now, instead of just the outcomes of our operation, we have to keep track also of the settings. For example, which measurement basis do we decide to perform at measurement at time 1, at time 2, and so on. And there is actually a known object that is the classical version of what we need, which is known as a classical causal model, where we are not only looking at the probabilities for outcomes at a given time, we're looking at the probabilities for outcomes condition of, generally speaking, choice of intervention. So that's how you can model causal influence. Classically, you have to model the possibility of intervening on the system, and then correlations between interventions and outcome represents causal influence. In the quantum case, this is quite straightforward to understand what it means. Choice of intervention, as we said, is measurement settings, or more generally, choice of quantum operations. So this leads us to consider in more detail what are quantum operations. So now I will very briefly review the formalism of quantum operations to remind that what we're interested in is considering a scenario where we can perform multiple operations over time, and we want to model in general how different choices of operation can affect the outcome of our operations. So in general, a quantum operation is described as follows. We have an input Hilbert space, H, which we call AI for input, and an output Hilbert space output. And an operation is something that sends quantum states to quantum states, and at the same time leads to a classical outcome A. So the mathematical representation is a completely positive map. So it's a linear map from input to output states. And it sends positive states to positive states, also when you enlarge it to a larger system. Very particular example we're all familiar with is a projective measurement. So our system comes in, we project it with the state, and then we prepare the same state. Note that I'm not renormalizing the state. So MA of rho represented not normalized output of our operation. As a particular case, we should consider deterministic operations. So those where we don't see any outcome, or we can say there is just one possible outcomes, and it happens with probability 1. And so these are, again, completely positive maps, but additionally, they have the trace preserving condition, which means the trace of the state is preserved. And particular examples are, for the case of the projective operator, we can take the non-selective outcome of the measurement, which is taken by summing over all the outcomes of the previous measurement. But also a unitary evolution is another example of a deterministic operation. And now a very useful representation of general quantum operations that turns out to be very handy for the formalism is what is known as the Choi-Yamiokovsky representation. So instead of talking about linear maps or linear functions from input to output space, we can talk about joint operators in the tensor product of input times output space. The definition is the following, is given here. If you want to have a physical picture, imagine that you start with a bipartite system. So instead of just taking your input state, you have the input space and another space that is isomorphic. So if you're talking about 1 qubit operations, then you start with 2 qubits. You put them in a reference maximal entangled state, and then you pass only one through your operation. And then obviously what you get at the output is still a joint quantum state. And the useful thing is that now this state that you have at the output is in one-to-one correspondence with the operation. So this is an isomorphism. It has the very convenient property that completely positive operators, completely positive maps corresponds to positive semi-definite operators. And the trace preserving condition has a very simple mathematical expression. The trace over the output system is equal to the identity over the input. So this is a simple linear affine constraint that one imposes on these maps. Okay, so this is, in summary, the formalism of quantum operations. And now we are ready to introduce the quantum process. So as we were saying, we want to model general scenario where we perform a probability at time 1, time 2, time n. And I will not go through the derivation. You can either introduce this axiomatically, or you can introduce it constructively by considering the most general system environment Hamiltonian. Long story short, what we get is that we have a generalized Born rule. So if you want to know the joint probabilities for measurement at time 1, time 2, time n, then you can use this trace formula. So you take the tensor product of all your CP maps at time 1, time 2, time n, the Choi-Minkowski representation, and then you trace them with this object W, which is called the process matrix. So now this W lives in the tensor product of input and output spaces at all different times. And it has the following properties. It is positive semi-definite. And so in a sense, we can actually regard it as a kind of state over time. Now, I said earlier that we are not allowed to talk about state over time, but now we obtain a slightly different picture. At each time, we have both an input and an output space, which allow us to model arbitrary operations. And furthermure, this process matrix has to satisfy certain linear constraints that imply causal order. So if we want to impose the fact that future settings do not affect past outcomes, we have to impose a certain set of linear conditions on W, which means not all positive semi-definite operators will be process matrices. But apart from that, the connection with states is very strong. So formally, we have a formula that is very similar to the Born rule, and so we can use a lot of the things we know about quantum states and use them to study processes over time. And now this is an object that has been discovered and re-derived many times, and among the many names it is known with, it's quantum strategy, it's known as a comb, it's known as a multi-time process, a super density operator. I omit many other things like process tensor and quantum channel with memory. Just be aware that every few years or so, this object is rediscovered anew. Okay, so this is the basic formula. And now going back to the idea of tomography, is this the best description of our system over time? And the answer is yes. First of all, as we said, we have this formula for the probabilities, which means for any possible operations we can perform at time 1, time 2, time n, we can calculate the probabilities if we know the process matrix. But on the other way around, we can also reconstruct the process matrix from pure measurement. So without knowing anything about system environment interactions, if we select informationally complete operations at each time, then we can reconstruct the process matrix. Essentially, if you look at this formula, you see that the probabilities on the left-hand side are a linear function of M and W. And so if M spans all this, so the M operator span all the space of processes, you can invert this formula. So essentially, you can rewrite W as a linear function of the probabilities P. And specifically, a choice of informationally complete operations is at each time I perform a measurement, projective measurement on an informationally complete basis, and then I re-prepare pure states again in informationally complete basis. And this allows us to to use standard tomography techniques to reconstruct the process matrix. So we reconstruct the process from probabilities, and once we have the process, then we can use it to make predictions for any operations, including operations that we have never performed before. So this is the strength of tomography, that given we reconstruct the process, then it allows us making predictions also for new operations that, for example, we can perform unitaries or other type of measurements we didn't do before, and the process is still enough to characterize everything we need to know. This is, in fact, a relatively recent development, and just recently multi-time tomography on a superconducting qubit was performed. In this paper, we overcome some limitations that were present in previous works, and this is actually now a working tool that experimentalists can use. Okay, so this is the general theory. Now let's consider specific situations. In particular, what does it mean for a process to be Markovian? So I described the most general quantum processes that involve the most general system-environment correlations. Now, a Markovian process, well, now this is just a definition, but I think it's relatively intuitive. What we have in mind, okay, the rho at the beginning here is melts with the environment, with the background. But what you have in mind of Markovian is that it's a process that can be reproduced or it can be simulated without keeping track of any memory in the environment. So we have some initial state for the system, and then after the first operation, we have some evolution from time 1 to time 2, and time evolution from time 2 to time 3, and these are completely independent evolutions that can be specified one by one. And the corresponding process matrix has this very simple form. It's proportional to a product state. And so these so rho AI is the initial state, and T1 is the Choya-Minkowski representation of the evolution from time 1 to time 2, and we just take the whole product. And the fact that this is a product represents statistical independence. So as I say, the fact that evolution between each time step is independent from evolution at any other time step. And an interesting concept that one can explore given this formalism is that of classical memory. So what is classical memory? Well, it's the next thing from after quantum memory, after Markovianity. So here, consider the physical scenario where you have a process, which again, you're going to probe at time 1, time 2, time n. And now there are some correlations between evolution at different times. But now consider the particular case where it is sufficient to keep track of classical information at each time. So most generally, we have in mind that we start with some system, with some state of our system, but we don't know exactly what system it is. We have some classical random variable that tells us what is the initial state. And then these classical random variables also correlates with the evolution from time 1 to time 2, and from time 2 to time 3, and so on. So a very convenient result that comes from this formalism is that if you have such a classical memory, then in particular, you can write your process matrix as a separable state. So it's a convex mixture of product states. Now, this is not an if and only if, in the sense that if your process has this form, it doesn't necessarily mean it has classical memory. And the additional detail is that when you have these M operators, in this form, they're not guaranteed to represent evolution from time 1 to time 2, time 2 to time 3, and so on. So in particular, if these are trace-preserving maps, then you will have a process that is a mixture of Markovian processes. And you can have something a little more general with classical memory, which is between each pair of times. You can imagine the environment is effectively measuring the system, extracts some information, and then sending it to the future. And then the evolution at the next time step can depend on the classical outcomes that are kept in the environment. And then at the end, the outcomes in the environment are all traced out. Okay, nonetheless, it's very convenient that classical memory implies this separable form, because then we can use standard techniques that we know from quantum states. So in particular, so now remember that our process, our multi-time process, is isomorphic to a multipartite state. So for example, if we were looking at the 1-2 level system, then having n time steps means modeling this process as 2n qubits, one input and one output for each time. And the definition of classical memory implies separability across these particular partitions. So partitions that corresponds to the evolution between pairs of time. And now what we know is that even though, for example, Markovian processes don't represent a convex set, classical memory processes do correspond to a convex set. So this is the whole Venn diagram of the whole scenario. So just to maybe walk you through, we have the Markovian processes in the middle. These are product states, essentially. We have a classical memory processes as I described. Combs are the most general causally ordered processes, so include classical memory in particular. And separable states are those that are mixtures of product states. And as you see, there is a non-trivial overlap because, as we said, some separable state might not correspond to classical memory. However, what we can do from the theory of entanglement, that we know from the theory of entanglement, we can define a witness. So a witness is an operator, which is defined by the property that if you take the trace of the operator with an operator if you take the trace of S with an operator that is separable, so inside this separable set, then it gives a non-negative number. And so geometrically, you can interpret this witness as a line that separates the set of separable states from the other side. And so the point is that now, if you have if you see that the trace of an operator S is negative, this implies that our process has quantum memory. So it implies that it's outside the set of separable states, which in particular means it's outside the set of classical memory, which means it has a quantum memory. So this is not an if and only if. So you see that there is this line, and so you can also have processes that have a quantum memory that falls on the other side of these lines. And then it's, of course, a general question from entanglement theory, how to optimize your witness to detect entanglement, in this case, quantum memory for a particular operator. Now, this is a mathematical definition of witness. However, it turns out that these operators S actually corresponds to laboratory procedures. So in general, I was describing the situation where we perform measurements at time 1, time 2, time n. One can imagine more general measurement procedures where the measurement at time 1 is correlated with the measurement at time 2, correlated time n. And in general, you can construct any operator on this joint system can be constructed from such a sequence of measurements. So the point here is that we have a well-defined experimental procedure to decide if a process, to witness if a process has a quantum memory. And as compared to tomography that I discussed before, this can be more convenient because typically tomography requires a very large number of measurements, while here it could be a smaller number of measurements if we are only interested in witnessing the quantum memory of a particular process. Okay, so this was a very broad overview of the formalism. So I will quickly recap what we discussed about, give an outlook, and then there will be time for questions. So as we said, we found what is the best description of a quantum stochastic process or of a process evolving over time, and this is the process matrix. And as we said, this an important insight is that this process also models causal influence, in the sense I'm allowed to change the operation I can perform at each time. And the process encodes the causal relations between choice of operations and measurement outcome. And in particular, arbitrary non-Markovian correlations across multiple times can be modeled through this process matrix. Now we say that non-Markovian noise is generic in quantum experiments. And so in applied scenarios, we cannot go around the situation, and we need this type of processes to describe our devices. And in particular, I introduced the concept of tomography. which means even if our system environment interaction is very complicated and we cannot model it theoretically, we can in principle perform tomography. And of course, in most applied situations, we will have probably some middle ground where we have some information about our system environment correlations, which hopefully would allow us to characterize the system without the full tomographic reconstructions, because this can be very expensive if you consider many, many times. The number of measurements you have to perform increases exponentially. And so this is a relatively new field, and so there is still a lot to do in terms of optimizing the tomographic procedure or the type of reconstruction procedure based on prior information about the process. And as one possible application of the formalism, I discussed quantum memory, which we have seen is formally equivalent to, well, not really equivalent, but can be formally mapped to entanglement. And this allows us to use known tools from entanglement theory, such as witnesses. And so we can define operationally well-defined quantum memory witnesses. Something I have not discussed, this whole formalism can be generalized. And well, I will not discuss in detail why it's interesting to do so, but at least at the formal level, you can relax the condition that our measurements are performed in a sequence of time. So time 1 before time 2 before time 3. You can consider more general processes with where the order of events is not defined. And there is a whole formalism, there is a whole framework to discuss to treat indefinite causal order. And finally, what I discussed so far is only scenarios where you perform discrete measurements. And the assumption here is that the measurements you perform take place on a time scale that is very short as compared to system environment interaction. And one of the things I'm currently working on is to generalize this to continuous time processes and continuous time operations. And with this, I will thank you, and our observer thanks you. And I think we have quite some time for questions.
Thank you, Fabio, for your text. Let us thank him. Now it's time for questions. So questions from Andrei Semyonov.
The microphone. Maybe I can use this one. Yeah.
I can hear.
Turn it on just a moment.
Yeah, thank you very much for your nice talk, Andrei Semyonov from Kiev. I have just one question. If you have a tomography of an unknown process, unknown quantum process, and after that you want to conclude either your process is Markovian or non-Markovian, do you have some tool how to do this, how to make such conclusion?
Yeah, in general, it's not completely easy, but there is in principle it's always possible. So, for example, if you have your process, you reconstructed this, now it's an operator, and essentially it's a mathematical question, is my operator a product or not? So for Markovian, you cannot use witnesses because the set of Markovian processes is not convex. Well, you can still use witnesses in the sense if, for example, you show that you have quantum memory, then you know that you're not Markovian. But if you want to prove that your process is Markovian, you cannot use that. However, you can use tools. You can use numerical tools or optimization tools to test if you're. In particular, in this case, there is a simple test you can make. You take the reduced process. So if you have a general operator W, then you calculate all the marginals. So rho A is what you obtain by tracing out everything, and then T A O B I, what you get from tracing out everything. And then you compare your original operator with the product one. And if it's the same, it's Markovian. If it's not the same, so for example, you take the norm distance or any other type of distance. If the distance is not 0, then the process is not Markovian. If it is 0, it's Markovian.
Just an additional, what is the best distance between operators? In this case?
It depends on purposes. So the one we typically use is relative entropy. It has some good information theoretical properties. It's not always the best for calculational purposes. I would say the simplest one to use is Hilbert-Schmidt, is the norm distance. You know, trace of W minus W prime square.
Okay, thank you very much.
Do you need some quantum metric in this case concerning the question of Andrei?
You mean to describe the geometry of these processes, of the space of processes?
Okay. So, more questions online? Oh, Larissa.
Naive question.
Okay.
Fabio, thank you. I have a naive question. Can you say that tomography say it is a kind of the inverse scattering problem like we use in quantum mechanics in many other respects? Tomography, you use tomography. Is it a kind of inverse scattering problem?
Inverse scattering. Let me think about it. So how do you think about inverse scattering? That from scattering you calculate
reconstruction of the system from the measurements.
Yeah, I guess you can see it this way. So maybe if you want to make the analogy a little shorter, I think you can speak it this way. So you can think of this, one way to think of these multi-time operations, you can think of a collisional model. So you think that at each time you sending a probe system which scatters or interacts with the process, and then you have a different probe or a different particle at each time. And so in some sense, you can think of it as a multiple scattering problem. It's a bit more generalized in the sense that the scattering can be an arbitrary interaction, but yes. So I think you can view it this way. So you're scattering multiple probes with the same system, and then you reconstruct the process from the outcomes of all the scattering all the scattering probabilities.
Okay, thank you. That's for better understanding of your field. Thank you.
So I don't see any questions from auditor here. Maybe someone online has questions. I don't see. No. So we don't have more questions. So let us thank our speaker again.
Thank you.